These are the factoring review notes. Now, factoring is a really large part of this class. We will be factoring all year long. We'll be factoring polynomials pretty much throughout the entirety of first semester. We'll start learning how to factor logarithms in second semester. And we may get to the point where we start factoring trigonometric functions in the spring. Not sure if we're going to get that far. However, if we do, we're still going to be factoring. There will still be algebra involved in some of the trig equations where you will need to factor. So factoring is kind of one of these year-long skills. It's one of these things I absolutely have to touch on and absolutely have to bring this review in. If you are struggling with it, please ask me questions on this. This is one of the biggest things where I want you to ask me questions on it. If you are struggling, let me know. We can work this out. I've got a ton of different ways that we can help. We can get practice. But if we are not solid in this skill, the year is going to be a little bit of a struggle. So we really, really want to solidify ourselves here. All right. So old school factoring, you guys started doing this in like 6th grade. It was when you were just finding the greatest common factor of two numbers. So you were breaking two numbers down and trying to see what's the largest number that they have in common. If we look here, I've got two examples here. So I've got example A, which is kind of what you were doing, maybe even as early as like 5th grade. You just have two numbers and you're looking for the largest number they have in common that multiply to make it happen. So when I do this, I'm going to break it down, and I'm not going to find, when you find factors, it's going to be really tempting to break it down into numbers that you know. So like 9 and 9 and then 9 and 6. But the issue here is that if I break it down into numbers that I know well, I might actually end up missing the greatest common factor. Sometimes there's numbers larger than the numbers I know right off the top of my head. I've made this mistake many times. It's a common mistake, and that's okay. But we do want to practice the skills that are going to make it so we don't make the mistake as often. I see 81, and I realize that 81 is divisible by 3, and it's the smallest number 81 is divisible by. This allows me to actually kind of break down the factors a little bit more. I've got 3 and 27. Before I start breaking this into further factors, I'm going to wait and see what happens with 54. 54 is even, so that means I can divide it by 2. That's always a really good approach to take, is divide your numbers by 2 if they're even, and I get 27. Well, right away, I've already seen the greatest common factor they have. I now know the greatest common factor between these two is 27. Had I worked through and found all of the factors, breaking down 9 and 9, 9 and 6, it would have ended up giving me all these small numbers. I would have had to do some multiplication. I would have had to follow a bunch of weird little rules. If we break it down, and this is what we call a prime factorization, where you divide by the smallest divisor of prime numbers you know, then you will end up getting your greatest common factor a lot quicker. You don't have to remember any weird rules or steps or anything like that if you just always divide by the smallest number you can think of. Once you get to 7th and 8th grade and we started learning variables in pre-algebra and algebra, the greatest common factor became a little bit more complicated. We started looking at it and saying, let's not just look at numbers. Let's also look at variables. So again, one of the things I'm going to do is I'm going to break down 144 first, and I'm going to divide it by 2, and I'm going to see that the factors there are actually 2 and 72. Remember that I can consider 1 a factor, so that means that 72 numerically is going to be my greatest common factor here. So I go through and I say that, all right, I now know 72 is going to be part of my greatest common factor. However, when I have variables involved, my greatest common factor also has to involve variables too. And again, I reviewed these a little bit when we were doing the expanding polynomials, but remember our exponent rule that if I multiply two exponents, so if I have like x to the 3rd times x to the 4th, you add them together to turn them into x to the 7th. Or x to the 7th consists of x times x times x times x times x times x times x. So we've got 7 x's that turn it into x to the 7th. With that in mind, when I'm finding my greatest common factors, I see that my lowest exponents for x is 1. And they both have an x in common, so that means that it's 72x. Both of them have at least a y squared. So that means that y squared is my greatest common factor. 72x squared y cubed, there's obviously 3 y's, but 144 only has 2 y's associated with it. And then finally, based on that first term, we're limited to 1z. So my greatest common factor here is 72xy squared z. Again, it gets a little bit more complicated there when we're looking at the variables, but it's still just based on that ability to break those down. So we can factor binomials. Whenever you see a binomial factored, there's like a 50-50 shot that you're going to be doing a greatest common factor. The other real option would be either a difference of cubes, which we're going to touch on a little bit later, or a difference of squares, which we're going to see today. So when I factor this binomial, this means that I'm going to think about greatest common factors here. I know that 6 and 18 both have a 6 in common. I know that both of these have an x in common, and I know that they both have a y in common. Now I'm going to put parentheses, because what I'm doing is I am reversing the distributive property. So when we looked at the distributive property, when we looked at expanding polynomials 2 nights ago, now we're just kind of reversing that process. When I multiply 6xy, I ask myself, what do I have to multiply 6xy by to get 6x squared y? Well, x is the first term, and then the other term is going to be 3. 3 times 6xy becomes 18xy, x times 6xy becomes 6x squared y. And then I end it here, and this is my factored form. Now the nice thing about factoring is you can always go back and check yourself. We can do that polynomial expansion, which we reviewed earlier. I can take 6xy, I can distribute it to 6x, and negative 3, I get 6x squared y minus 18xy, and that checks out. So that means that my expanded factors match my original binomial. So I factored by greatest common factor accurately here. The next thing we have is factoring trinomials, and this is where it starts getting a little bit more difficult. Our first brand of trinomials we can factor don't have anything in front of x squared, so that means we just have a 1 in front of x squared. These are one of the easier trinomials to factor because right away I can just start off my first term with x's. If I don't have any number in front of x, my life is really easy because I can just put 2 x's down for my factors. The next thing that I have to do here is I'm looking for numbers that multiply to c and add to b. And what do I mean by c and b? I mean that trinomials are expressed by ax squared plus bx plus c. So I'm looking for numbers that add to this third term here, and they multiply to the third term. I apologize. They multiply to the third term, and then they add to that second term. So I start thinking of factors of these numbers. Okay, well, I've got positive 6, and I've got a negative 5x. So then there's another set of rules that I'm going to write down to kind of help us with that. If c is positive and b is positive, your factors will look like this: x plus times x plus. If c is negative and b is positive, then your factors will look like x minus and x minus, because we'll have 2 negatives that multiply by each other to make a positive, and then those 2 negative numbers will add to make a negative. And then finally, the last rule will be if c is negative, then your factors are just x minus and x plus, because you're going to have a difference of signs. Whenever you have a c, whenever you have a negative c, you have to multiply by opposite signs to get there. So I've got a negative in the middle, and I've got a positive at the end. So my b is negative and my c is positive. That means I'm looking at 2 negatives. And then I ask myself, all right, negative 6 times negative 1, but that adds up to negative 7. The only other option is negative 2 and negative 3. They add up to negative 5. So my factors here are x minus 2 times x minus 3. I can go back through and check myself by writing those factors out and then distributing. I get x squared minus 3x minus 2x plus 6, and I get x squared minus 5x plus 6. So I factor this correctly. I feel really good about myself. I like the fact that I'm checking my work to confirm it. All right, we're going to do another example here. So again, I've now got a negative at the end. So since I have this negative c value here, I know that immediately I've got a z plus and a z minus. My next clue here is that I've got a positive 13, so my b value is positive. So that means that whatever I put as my plus has to be the larger number. So I started asking myself, what are some things that multiply to make 68? Well, 34 times 2 is 68, but that's not going to get me anywhere close to 13. So 34 times 2, 68 could also be divided by 4. So if it's divided by 4, that's 17 and 4. Oh, well, 17 and 4, if I have a positive 17 and a negative 4, that adds up to negative or positive 13. So now I've got z plus 17 times z minus 4. I'll go ahead and check my work really quickly. I distribute both of my z's. I get z squared minus 4z. I've got plus 17z minus 68. And I've got z squared plus 13z minus 68. The biggest problem with this is there's a lot of guess and check involved. And I understand that. That's just kind of life with factoring. I can recall sitting, working on my homework in algebra 2, precalculus, everything. Anywhere where I had to factor, I would sit there, and there were so many times that I would be plugging numbers in on my calculator, working on problems 2 or 3 minutes. Eventually, I got faster, and it got to the point where I didn't need to think about factors as much. But even now, sometimes I'll get really, really stuck on a factor, and it'll take me 2 to 3 minutes to figure out the numbers that work. That's okay. Sometimes it doesn't come naturally. Sometimes it's a little bit obscure. But when we practice the skill, we get better at it and we get faster at it. All right, we can also combine some concepts. So I'm letting you know that I'm combining GCF and trinomials here. Textbooks aren't always going to be that nice, but we want to try to recognize it as much as we can. So here I see that all of these numbers could be divided by 3, and they all also have a z in common. So I'm going to take 3z out at the beginning, and when I do that, I'm left with x squared minus 6x minus 17. 51 divided by 3 is 17, yes. So I'm asking myself what numbers multiply to make 17 and add to negative 6. 17 is a prime number, so that doesn't work. I'm going to check myself really quickly on my calculator to make sure that I divided this correctly. And yes, it is 17. So I've given you something that once you take out the greatest common factor, it actually is unfactorable. That is on me. However, we have 3z times x squared minus 6x minus 17. Had this been a trinomial that you could factor, we would factor beyond it, and we would make sure that 3z's multiplied at the beginning too. So let me change this to something that I actually think is going to work. Let me write up a new example right off the top of my head. Let's call this 3x squared z minus 18zx, and then let's say minus 54. So I've got, I'm going to take out 3z. We'll turn this into x squared minus 6x minus 9. Minus 18, I apologize, minus 18. Now I'm trying to figure out numbers that multiply to make negative 18 and add to negative 6, which yet again, this is unfactorable. So I've now left you with 2 unfactorable trinomials, so I'm going to stop trying to make this work. But we could end up with multiple factors here. Trying to think off the top of my head if I can salvage this somehow. Okay, we're going to do one more example because I really want to show you what the end result is here. Just be patient with me, guys. So I've got 3x squared z. We're going to do minus 21zx. I now know for certain this one's going to work. This is how math teachers work sometimes, is they go through a lot of practice and they realize the numbers they created don't actually work, and then they have to go back to the drawing board. So here I've got 3z. I can pull 3z out of everything. Now I have x squared minus 7x minus 18. Now I can actually figure out some numbers that multiply and make negative 18 and add to negative 7. So remember here I'm going to have an x plus. I'm going to have an x minus because I'm going to have a negative times a positive. Negative 9 times positive 2 makes negative 18. So that means I've got x plus 2 and x minus 9. And my final factored form looks like this. So I have to include the fact that I took that 3z out at the beginning, and then I factor my trinomial normally. So I want to make sure if I factor out multiple terms like that, I still keep everything at the end. When I pull out that 3z, it doesn't disappear. It doesn't float off into another dimension. It stays part of the factor, so you have to include it at the end. A difference of squares, this is a special polynomial, or a special polynomial we can factor. The rule is if you have a squared minus b squared, it becomes a plus b times a minus b. This is something that you're going to see all the time in math textbooks. Mathematicians and math textbook writers love difference of squares to put that in, include it. So you really have to be aware of what your squares are. What does this mean? That just means I look at my first term and I try to figure out 81x squared. 81x squared is equal to the entire term 9x squared. So that's going to be equal to a squared. 9x is equal to a. I see that 16y squared is equivalent to 4y squared. So that means 4y will be equal to b. So then I have this formula of difference of squares. This is just a pattern that always occurs. So that means I plug in, I've got 9x plus 4y, because I put the a's where the a's go and the b's where the b's go, and then I've got 9x minus 4y. And now I factored this as a difference of squares. This is a really common pattern. I'm going to be including this in so many quizzes and tests. The quicker you can pick up on it, it saves you a lot of time and a lot of heartache and frustration. So recognizing it is really good for you. All right. Finally, the last thing we have going for us is factoring when a is greater than 1. So what I mean there, again, we've got ax squared plus bx plus c. It's really nice when we don't have anything in front of that x, because that means I can just leave it blank in front of the x. My number's an assumed 1. When I have an a value greater than 1, though, when I have a new number, it makes my life a little bit harder. Now, we're going to factor by grouping. I'm sure you learned this in Algebra 2, but sometimes it's complicated. It can be a little bit frustrating, but now that we're going to see it for the second year, it's going to help us out. When we factor by grouping, our first step is to multiply a times c. So that means I'm going to multiply 6 times negative 2, and that's going to give me negative 12. Now that I have that, I'm going to go through my normal process. I'm going to figure out numbers that add or that multiply to negative 12 and add to positive 1. Well, the numbers that do that are going to be positive 4 and negative 3. When we multiply these out, it gives us negative 12. When we add these, it gives us positive 1. So now what I do is I take my numbers and I say 6x squared, and I take these numbers that I just found, that negative 3 and that positive 4, and I include them. So I'm going to say minus 3 plus 4, and then I'm going to keep that original minus 2 up. I'm going to ignore the 12. I just use the 12 to find my middle numbers. I can't leave my middle numbers as is because that's not the way it is. I had an x in the middle somehow, and I found that my x in the middle was created by adding a 4x and a negative 3x. Now that I'm here, I'm going to group these together. And I've already put these together in a way that's going to group well. Again, sometimes you're not going to put the groups together perfectly. That's okay. You get better at it with time. Usually working with prime numbers that are very similar helps. Like I know 3 and 6 are both divisible, 4 and 2 are both divisible. I know that 4 and 6 are a little bit less divisible than 3 and 2, so I'm going to take a stab with numbers that are divisible by 3 and 2 first. I can pull a 3x out of my first term, and I'm left with 2x minus 1. And I can pull a 2 out of the second term, and I'm left with 2x minus 1. Now, factoring by grouping works when when what's left in those parentheses is the same term. So since I have 2x minus 1 in both of these, that means that one of my factors is 2x minus 1, and then I take whatever is left over, and that becomes my other factor. So I've got 3x plus 2 times 2x minus 1. And that's my final answer. I can still go through and check this like I have been prior. So I've got 3x plus 2, I've got 2x minus 1, and I distribute my terms. I get 6x squared minus 3x plus 4x minus 2. And would you look at that, this is the exact same term we had before we combined like terms as we had up once we figured out those factors. Once we multiplied a times c and found those numbers in the middle. So basically what we're doing is factoring by grouping is kind of taking literally the reverse of expanding this polynomial, figuring out the middle step, and then breaking down our factors from there. Because this becomes 6x squared plus x minus 2. So we found that same trinomial that we began with, but we factored by grouping. I think this is really, really cool to look at because now we can see that this line is just very, very similar to this line over here. And not that line, sorry. This line up here. And by very similar, I mean exactly the same. We're just kind of breaking down what is our expansion and then working backwards step by step. I've got one last example. Here, I want to figure out what's going to happen. I see that all of these are divisible by 5. So since they're all divisible by 5, that means I can factor by greatest common factor. I'm left with x squared minus 10x plus 12. And I want to ask myself, all right, what numbers multiply to make 12, but then add to make negative 10? Well, I think we might be kind of stuck on this one because you can't multiply. Positive 6 and positive 2 makes 12. That does not add to 10. Positive 3 and positive 4. 12 does not make 10. Positive 1 and positive 12 does not make 10. So here is just factoring by grouping, and we would have to leave it as so. So sometimes when you're given factors, it looks like you might be able to do more, but sometimes it's just breaking it down by factoring by grouping. So you've gotten examples for everything that's on tonight's homework. Tonight's homework is 2 separate worksheets. It's a lot of factoring the trinomials because you're going to be factoring trinomials more than you factor anything else. Again, this is really, really important that we have this skill down solidly. So if you have any questions or concerns, if something's not clicking for you, reach out to me sooner rather than later. We can also set up Zoom meetings over the weekend if need be. Come talk to me if you have any concerns. We can find a time to meet. Don't let the fact that this year looks a little bit different prevent you from coming and talking to me. So everyone have a great night and have a great weekend.